Good day everyone. Today we will be exploring two key mechanical properties of materials. The outline of today's video will be defining elasticity and plasticity, finding the critical points of the stress-strain curve, and solving some practice problems. Elasticity refers to the ability of a material to return to its original shape after experiencing force. This force results in temporary deformation, but can quickly return to the original shape. In contrast, plasticity refers to the tendency of a material to not return to its original shape after an application of force and experiences permanent deformation. Before delving into the stress-strain curve, we recall Hooke's law. This law states that the force acting on an object is proportional to the deformation it experiences within the elastic limit. This law can also be taken under the perspective of stress and strain by manipulating the variables to see here, wherein E is the modulus of elasticity, or Young's modulus, which shows the relationship or slope between the stress, represented by sigma, and the strain, represented by epsilon. This law applies to the first part of the stress-strain curve, from point O to point A. In this case, the stress the material experiences is proportional to the strain. Point A is referred to as the proportional limit. This is a unit of stress that marks the limit where Hooke's law is observed when a material is subjected to stress. From point A to point B, the relationship between stress and strain changes as observed by the shift in the slope on the graph. This is why Hooke's law cannot be applied anymore. However, it is important to take note that this region still falls under the elastic region. Point B is what we refer to as the yield point. This marks the divide between the elastic and plastic region of an object's response to stress. The stress at this point is referred to as the elastic limit. Beyond point B is the plastic region. The object already experiences permanent or plastic deformation. As such, it cannot return to its original shape, as shown on point C, wherein the object, after experiencing deformation, tries to return to its original shape. If the object experiences more stress, at some point it will fracture. This fracture point is point D. The stress at this point can be referred to by a lot of terms, such as fracture stress, breaking stress, ultimate strength, and tensile strength for tensile stresses. The stress at this value is critical since it is used to establish a factor of safety. This factor of safety is a multitude of the strength and is usually employed when designing for critical structures or machinery reliably and safely. The stress-strain curve can also tell us about the nature of a material. For example, when a material experiences a large amount of stress between the elastic limit and fracturing, we refer to it as ductile. On the other hand, when it can only handle a small amount of stress between the elastic limit and fracturing, we refer to it as brittle. There are some materials that have elastic regions that do not conform to Hooke's law at any point. When a material follows different curves for increasing and decreasing stress, this is called elastic hysteresis, such as in the case of vulcanized rubber. In this case, the remaining energy is dissipated through heat or by virtue of internal friction. This is good for dampening shocks and vibrations. With that, we will now be delving into the first practice problem. A metal solid cylinder is subjected to a universal testing machine to check its tensile strength. The recorded tensile strength is 400 MPa. Determine the tensile force needed to break the cylinder if the diameter is 10 mm. In this problem, we are given the stress, which is 400 MPa, and the area via the diameter. We have to calculate for the area using the diameter, using the area of the circle equation. After this, we can calculate for the force. Here, we take note that MPa is newtons over mm squared to make things easier. From this, we have a force of 31,416 newtons. For the second problem, a wire of a certain material is used to drag a boulder vertically. The elastic limit of the wire is 1 MPa. Determine the minimum wire diameter that will not experience permanent deformation if the boulder weighs 500 kilograms. In this problem, we are given the stress and the force. So, we have to calculate for the area. The area can be calculated using the area of a circle. From this, we can get the diameter, which is 78.99 mm.